Dear all, before we start with practical, real work and workshop, I wanted to say some inspirational and motivational words. I'm the motivational speaker of this event. So I remind you that we still have groups. I know that in the last few days there was not much time to really meet in groups, but if you are not extremely too tired, I still suggest that after this event you gather in groups and have some chat with humans for a short while and just state your best and hardest things and also write it in the document. And I also wanted to hint already towards tomorrow that in the closing session we will also look back not only what we learned, but I would like also us to think about how we felt and what was the process. And that's partly also the meaning of this well-being file. And that comes from my experience in technology, that unfortunately it's not only about what you learn, but also about managing your well-being and thinking about the process and how you learn and how you not overlearn. And okay. So, but with that, I hope we're having one more exciting session today, and I pass mic to Normund.
Okay, thank you, and welcome to this afternoon workshop on creating and analyzing multilingually comparable text corpora. And indeed, I hope we will do all these things. We will create a corpus altogether. We will also analyze some data that we have created, and it will be multilingual, since I guess that you are representing here quite a lot of languages. Yes, and this will be mainly about text analysis, so rather linguistically oriented, but yeah, we will see. And I guess that you are not all linguists here, but still. So our team, my name is Normund. I have two hats. One is that I'm head of Artificial Intelligence Laboratory at the Institute of Mathematics and Computer Science, and I'm also teaching at University of Latvia. And then Arturs, who is a researcher and also our most experienced research engineer at the Artificial Intelligence Laboratory, and also our assistant Viesturs, who will help us here with the practical assignments, who is also a research assistant at the laboratory and a teaching assistant at the university. Yeah, well, maybe a few quick questions to you to better understand our audience. So how many of you are linguists, or more or less linguists? Okay, that's good. Not all, but quite a few. That's good. And so I guess that you all have more or less experience with using corpora, querying, etc. Have you also worked with tree banks? What's that? Okay. So tree banks, no one? I know that at least two of my colleagues there. Okay, then you will learn something new. We will not actually work with tree banks, but some syntactic concepts will appear. So, also, this workshop is aimed mostly at those who yesterday and the day before took the Python basic course. So those who are intermediate or advanced programmers will for them those tasks will be very easy, but then you will be able to surprise us with some extra work from your side. So this workshop is intended as a slow pace, hands-on, so that less is more principle here will be used. Okay, so let's start. So the agenda today. So first of all, we'll start with a showcase to put this all in a context why we are doing, why we will be doing all this hands-on work, and I will show you one such demo, which is the parliamentary corpus called Parliament, which hopefully will motivate us to do all this practical work. And also through this specific corpus, as an example, we will notice that there are some syntactic notions that we will base on queries on. And so we'll also take a little glimpse on what is universal dependencies. Has anyone heard such collocation? Oh, okay, great. All right, and then when this conceptual foundation will be laid, so I'll also explain more concretely what will be the task for this workshop and what will be the toolkit that we'll use. But then Arturs also will tell us, will put this in a context of this summer school. So the summer school is about large language models. We will not directly be working with language models, but language models will be in the engine room while we will be using those high-level toolkits. Not the very large language models, therefore this letter A has dropped a little bit because we will use small-scale, cost-effective language models for not that much for language generation, no, for language understanding, the other direction. But we will see that such small-scale language models, which are basically do not cost us anything to run them, can be very powerful for doing a specific set of tasks and solving specific set of problems. And then this hands-on work after this introductory lecture will be, well, it will be consist of 3 parts, so to say. First of all, we will get our hands dirty because, well, to do the actual work, you have it's typically that you have to collect data, you have to pre-process this data, and this is a very tedious, time-consuming, not that interesting work, but it's inevitably part of the business. And then, when the data set will be prepared, we'll do the actual work and go from this unstructured text to structured data, and therefore we will use those readily available toolkits. And I hope that you will be surprised how easy we can do this actual work when the dirty work has been done. And hopefully you also have time to enjoy the fruits of our work, so that you will be able also to query the results. Okay. So this showcase. So there is such a European level research infrastructure, Clarin. Well, I guess that at least part of you have heard of this, but nevertheless, it's not that important. But within this infrastructure, there are several flagship projects, so to say, and this multilingual parliamentary corpus or set of several corpora is one of them. And we will look at this example because what we will do in this workshop, we will try to create a very small version of something like this. We will not work with parliamentary data, but nevertheless the idea will be pretty similar. And so this parliamentary corpus, it consists of many corpora for covering 29 countries across Europe, which means, well, most likely more or less the same amount of different languages. So typologically very different languages, of course. But to create this comparable and interoperable corpus, so they have used an annotation schema or standard or format that makes all those 29 different corpora comparable, so that you'll see that we will actually be able to run the same queries against different languages, different corpora. And this common format, this common grammatical format will be those universal dependencies that I mentioned before, and I will show you them in more detail later. So this interoperability is kind of one of the core aspects of FAIR research nowadays. So I guess that you have heard this FAIR set of principles that your research or research results, data sets, for instance, have to be findable, accessible, interoperable, reusable, and so on. But this interoperability will be a key aspect for today. And the universal dependencies as a general framework will help us to do this from the linguistic perspective, but we will also see. We'll also work a little bit on the technical details here, how to make an actual corpus which can be actually uploaded to a corpus platform and queried, and therefore we will work with some technical interoperable formats as well. A little demo from this Parliament set of corpora. So what you see here on the slide, so this is a parliamentary corpus from Great Britain, as the title says here, and here are some query results according to this pattern or query that is given here, and And at the end of this workshop, I hope that you will also be able to run queries like this. But just to explain very generally what's happening here, so from the linguistic perspective, so we are asking this corpus query engine to find all occurrences of words that meet such criteria. And these are those criteria for the keywords that we are looking, those occurrences. So first of all, this word should be a syntactic object to some. So that the syntactic function for this word should be object. The part of speech should be either noun or proper noun, not pronoun, for instance. Then this word should syntactically depend on some verb in a sentence. So basically, we are looking for objects of predicates or in a sentence, and this predicate or this verb should be, in case of English, the verb support. So essentially, what we are trying to find here are what the British Parliament has been discussing, what kind of support of giving support to what or to whom, and so here are some examples: support people, support war, support Poland, support Ukrainians, etc. But then, among those 29 corpora, so here is the Latvian corpus that we have prepared for this multilingual set. And without going into details, just see those slides as an animation. The only thing that changes in this query is this verb. Support in English, adbalstīt in Latvian, and my guess by using Google Translate was that in Estonian this word might be all right. But otherwise, this is well, the same query. Nevertheless, those languages are very different, but we are still using this very general syntactic term of object, these very general morphological categories like noun, pronoun, proper noun, and verb, and it works. Okay, and so this was one kind of an example that a common representation helps us to work with different languages and different corpora using the same queries. Also for Latvian, we have created the so-called Latvian National Corpora Collection, which again is not a single corpus. It's actually already a collection of 39 corpora and growing. This number is constantly growing. There are many institutions involved, lots of different corpora. Some of them are hosted at our institute. Some of them are hosted here at the National Library of Latvia. But they all are annotated using the same unified formalism and format. Morphosyntactic annotations are the same. The same syntactic parser is used here. Well, in case of Latvian, we can say that, well, okay, we can use some language-specific toolkit for this and we'll be fine. But in case of a multilingual corpus, so we need that the chosen formalism really works across languages. Okay, so we will not look under the hood what actually means to do part of speech tagging from the technical and implementation perspective, but just from the bird's view. So to get such a morphologically and syntactically annotated corpus, we need some tools for this. And typically, this tool set consists at least of two such tools. One of them is part of speech tagger. So the morphological analysis comes first. Well, kind of naturally. We also do similarly, at least we did at school, that we had to assign those part of speech categories to words and then draw some arrows how those words are related in the sentence. And this will be the parsing part. But first of all, this part of speech tagging and lemmatization, this is the first task, which such a language model must learn to do automatically. And well, the state of the art for such part of speech taggers for many languages, including Latvian, Lithuanian, Estonian, and other smaller languages, is above 95%. But then, again, since we are looking here from the multilingual perspective, there might be one tag set or one set of categories traditionally or typically used in one language, then other set of categories which is more applicable to some other language, etc. And also among different data sets, there might be the case that, well, for instance, in English, one data set uses names like noun or aux for auxiliary verb, verb for the verb category, etc. The other data set uses some other names for labeling the same things. NNP means noun, which is a proper noun. NN is just a noun. DT is determiner. So kind of the same but different names and maybe different number of categories, etc. But we will somehow need to get to a single tag set for all languages so that the same names are used for all languages and they fit them all. And therefore, we will need those universal dependencies. This is one thing. And then, when we are done with the part of speech tagging, when this first blue layer has been acquired by those automatic tools, or more concretely by a part of speech tagger, then the next task is to assign those syntactic categories or grammatical functions to each word in a sentence. There are different traditions, different schools, at least in the Baltic linguistics, this dependency parsing is more traditional. Maybe you can raise hands who is more familiar with drawing such arrows in a sentence from school, for instance, and who feels more comfortable about this phrase structure approach. One person. So the rest of you are not comfortable with any of those. Okay. Okay, so there are those two schools, two traditions. There are also technical differences and some pros and cons of each of those representations. But as you see, well, as we can see from this picture. This phrase structure approach means that we are trying to construct some hierarchical representation, syntactic representation of this sentence, of the constituents of this sentence. So the sentence, in this case, we say that the sentence consists of a noun phrase and a verb phrase, and this verb phrase is the whole will back the bill part. And then this verb phrase consists of a auxiliary verb and a nested verb phrase. And this nested verb phrase consists of a verb back and a nested noun phrase, which is the bill. But then the noun phrase consists of the determiner and the noun. So such constituency or phrase structure or context-free grammar approach. But then on the other hand, we have this dependency approach, which only tries to draw links without introducing any additional nodes in this syntactic tree. Just we are trying to draw the links, binary links between words in the sentence. So we say that this noun depends on the verb. So Janet depends on back on the verb to back, and is a subject in this sentence. And Bill is the object in the sentence, and so on. So no additional layers have been introduced here. But okay, this was just for the wider picture. What we will use, and we were already using in this example that I showed you, are those labels of the syntactic functions. So what this query contained previously was that we were looking for objects for such words in a sentence which have been labeled as objects to something, and this something had to be verb in that query previously. So we will work with this with these structures. And before universal dependencies, there were different formalisms for different languages, and they still are. But at least now we have some interlingual formats, so to say, to which we can convert all those language-specific representations. And these universal dependencies, well, historically. So first of all, this is quite a new formalism. First of all, there was an attempt in about year 2012. To come up with a set of universal morphological tags that would fit for all languages. Of course, fit not always very precisely. You have to make some compromises there, but still. So a set of universal tags, and this set initially was consisted only of 12 categories. Currently, there are already 17 categories, but this is what we will be using. And then on the other side, it turned out that also these linguistic functions also can be generalized across languages, and actually it's enough with 37 such syntactic relations or syntactic functions or roles to represent basically every language. And why I say every language? Well, not necessarily every, but at least currently there have been created about 250 tree banks already within this formalism, which covers about 150 languages. So it has been tested and approbated on quite a large number of languages, diverse languages. There are a lot of contributors to this initiative, and this is not only a formalism. There are also corpora created according to these universal dependencies guidelines, and these corpora are then used to train via machine learning language models that can specifically do this part of speech tagging, lemmatization, syntactic parsing job. And well, just to get the understanding, what does it mean to syntactically annotate a sentence. So this is more or less what it means. So you'd have to tokenize your sentence into words or tokens. And sometimes this single token consists of only one word usually, but it might be also several words if it's a multi-word unit or something like that. Then these lemmas or base forms are given, then this morphological tag, then some other more detailed morphological features of this concrete word, that this was used in the plural and etc. This word was used in singular in this particular sentence, for instance. And then these last two columns, these are not all the columns that could be annotated, but just the main ones. And then these last two, there is a number, and this number basically says that, well, there is an arrow from the first word in the sentence to the second word, and this relation between those words is that this first word is a nominal subject to this second word, which is a verb, and so on. And yeah, the work to make such a corpus, well, it takes quite a lot of effort, and my colleagues there, you can ask them about the actual work to create such a corpus. But so it takes a lot of effort, but when it's done, you can train an automatic model that will do this syntactic parsing for you, and surprisingly well. But what does it mean, surprisingly well? Also in the previous lecture today, there was this term used, accuracy. And of course, there will be inevitably errors in the output, but we still have to measure what is the level of accuracy and what we can expect from our model for a particular language. And for instance, there was a shared task in 2018, but it's only among other shared tasks where teams were trying to evaluate their methods and models, how well they perform on different languages using those universal dependency tree banks prepared by linguists. And for instance, for Latvian, which the Latvian tree bank at that time contained about 15,000 sentences. So this was the training set. And by using just those 15,000 sentences, well, it was already possible to acquire a parser whose accuracy is about 84%. So still quite a large gap of errors there, but this is already something useful. So we'll also have to keep this in mind, and it might be the case that when you will later on try to query the corpus, there might be the cases that, oh, but why I'm getting this result, this occurrence in my concordance list, this is not an object. Well, but this is because this parser works only with the, for instance, with the 83 or 85 or 90% accuracy, and even for English, well, it's above 90%, but it's not 100% at all. The second thing that you see from this shared task is that there are many different parsers created for multilingual parsing. In this slide, there are 26 different teams created their own parsers, some of them performing poorly, but many of them quite well. We will use in this hands-on session a toolkit called Stanza, developed at Stanford University. We will use it because it's very simple to use it from the programming point of view. Very simple API. As you can see, well, there are again more than 100 models trained for different languages. For some languages, several models per language. But for Latvian, we can see again. First of all, we need to look at the evaluation tables when we choose some model, just to to understand what is the expected accuracy. And we can see that for Latvian, this stanza model trained again on the same universal dependency tree bank prepared by our linguists already works a little bit better. So it's 86%, so 2% points better. Is it significant difference? Well, yes, most likely it is a statistically significant difference, especially in terms of error reduction. So the errors that have been reduced are much more than just 2% points. Of course, this stanza toolkit that we will use today is not the only one out there. There is, for instance, such a UD pipe, which is specifically developed on this multilingual set of those universal dependency tree banks, but it's not that easy to use it. It's a REST web service. It requires a little bit more programming, so therefore we will use this very easy to use toolkit, which already out of the box supports 70 plus languages for this syntactic parsing task. And there are some other toolkits that you could use. And then, of course, if you are aiming at a monolingual corpus, then maybe for your specific language, there is a significantly better parser out there. For instance, for Latvian, there is an LV pipe, and Arturs was the main developer of this toolkit, at least for the syntactic parsing part, and that language Latvian specific parser works with about 90% accuracy. So a significantly better model, but still, it's a bit specific implementation and integration from the integration perspective. Therefore, we'll use something very uniform that works for all the languages and is good enough. Okay, and now I will give the floor to Arturs to make some comments about what is going on under the hood.
Okay. Do you hear me? Okay. So I will try to give a very brief introduction to how we create these task-specific models and how we can automatically get these annotations from these models, and also how we can use transformer and large language models to create such models. So as Norman's already mentioned, that everything starts pretty much with data. For such tasks, we need well annotated, high quality data that is usually quite hard and expensive to create. It is a labor intensive task, and it also requires quite a lot of knowledge and systematic thinking about what we are doing in hard cases when it's hard to agree also for humans. And as Javier in his Tuesday talk already mentioned, that we have made significant progress since the days of basic machine learning, where we used statistical language modeling and manual feature engineering. We created lists for persons, for organizations, as features for name identity recognition. But nowadays, it has become much more simple. The models learn it by themselves. So as Javier mentioned, that from these statistical models, we went to models where we represent text as vectors, basically numbers, a list of numbers, with methods like word2vec. And nowadays, with the boom of transformer architecture, we can also learn not only just one vector per word, but we can have contextual word vectors. So the word river in phrases riverbank or river financial, riverbank and financial bank, the bank will be represented by different vectors, different to word2vec model. Right. nowadays, the part of feature engineering is not really that much relevant. We use already ready models that already kind of contains these engineered features. And what's left for us is basically select some model architecture that is appropriate for a task and basically train this model or fine-tune this model. And this process is depicted on in this picture a little bit. That basically we have inputs. The model has some weights in hidden layers, and we have an output layer. And basically the training works as we are passing data through the model. We calculate in the end difference between the actual outputs and the predicted outputs, and use this error to back propagate and change these model weights, so we can improve in the next iteration how the model predicts and adapts for this task. But maybe not to scare you, this training part nowadays it has become very simple. You basically can use the transformers library and just specify the model, specify the data and how to load it, and just run it. And in a few hours, depending on what size of model, you already can get some results. And of course, important part of this is also model evaluation. We want to measure if we are making progress, if a model does something meaningful. Otherwise, it's very hard to tell if we are improving really. Yeah, and then the model is ready for usage. Transformer-based models have really revolutionized the natural language processing. If we take a broad overview about them, we can separate them in 3 parts. First of all, there are encoder-only models, like BERT and its derivatives. They basically take input sequence and produce embeddings representing the text. This works very well for natural language understanding tasks, like text classification, token classification, etc. It considers the whole context of the input as a whole. So we don't look only on the left side of the word. Basically, we look on both these. These are bidirectional representations. So this is the most important point why encoders are very well suited for these natural language understanding tasks. However, the downside of these models is that they cannot really generate text. At least they are very limited in this capability. So if you want to unlock the knowledge that we have gained from training these models, we need to fine-tune them on specific tasks. The second is encoder-decoder, such as T5 and BART models. They are basically sequence-to-sequence models. They encode input sequence. For example, this is the best example probably is machine translation. We encode the source text fully, and then use the decoder to decode, looking at these source representations that encoded together with previously generated tokens, and that's how we generate the next token. Lastly, of course, are decoder models. These are GPT style family models, also Llama and other, and they are really language models in a sense that they are really conditioned on just the left context, and they generate next word in an auto-aggressive fashion that basically just looks at the previous word to generate the next token. We can control this, as we already have discussed in our workshops with prompting. It offers a wide possibilities of how we can use it, but it is also the downside of this model that it is hard to control because of if we change the prompt a little bit, the results will change, and also the input data from instructions from prompt is not very well separated. So it can create also additional problems for that. But this works very well for human interaction, but because you really can unlock the knowledge of model just using it. And we can fine-tune it even further for more specific tasks. As I mentioned, that for natural language understanding tasks, the BERT-style models are usually the go-to because they encode the text fully. The representations are bidirectional, they are really powerful because we can learn these models from large amounts of text and basically unlock this knowledge from texts that are just text. They are not labeled in any way. We can learn patterns and all kinds of relationships in language just from it. If you want to use it, as I mentioned, we want to fine-tune these BERT models to specific tasks. And because transformers are typically quite large, even though the BERT models usually are orders of magnitude smaller than the latest GPT-4 or other models, still it's not really practical to train them for each particular task. Instead, we just add extra few layers on top of BERT to basically use representations learned by BERT to classify, for example, is it spam or not spam in this example. This is an example of tensor learning where we can use a larger data set of even unrelated tasks. For example, as in BERT, we use mask language objective where we mask basically run some random tokens in a sentence, and the BERT model is trying to predict what was masked in this part of sentence. But it's using just this very, very simple objective, we learn very strong representations that can help also for classification tasks and other tasks. Okay. Yeah, and if you look a little bit deeper in these models, what exactly they are learning. Here we can see a very basic structure of BERT. It basically contains of multiple these encoder layers, and after each layer they have some representation for each token also and all the whole text. If we inspect these representations, we can see that these representations from layer to layer become more detailed, more nuanced, and usually what we are using for fine-tuning, these are the last layers that contains the most amount of knowledge. To the core of transformers architecture of why it can learn these contextualized representations is attention mechanism that basically allows to look at the different parts of a sequence on a sequence to make predictions. For example, we really can try to understand what these attention heads try to do, very often they are meaningful, basically things that the model is learning. For example, there could be position heads that basically looks at the previous sentence, previous token, or the next token, or start of sentence, end of sentence, or it could be content-based, that it looks for similar words in sentence or correspondent words in sentence. And in this concrete example, we have basically some kind of known modifier head that basically for words the and complicated, they attend to language, basically the nouns, the associate noun for them. Yeah, and it's quite surprising that the BERT model, without trying to learn, explicitly trying to teach it this kind of relationship, it learns it just from text. And this is why we can use these BERT models to use them really in small. If we have small amounts of data, we can force it to learn a lot of more than it already knows about intricacies of a language from these large texts. Yeah, just maybe for context, this kind of fine-tuning, it's like hours, but training like BERT from scratch, it could take days or orders of magnitude more. But it gives a real powerful tool in our toolkit to basically just with small amount of data, of course not so less compared to GPT, where we can just provide few examples, but this works really well in structured prediction, where we want to have very structured outputs. For example, as Norman's mentioned about predicting named entities, predicting dependency structure in sentence, etc. Okay, this will be it from my side. I will give word to Norman's about the task.
Yeah, thank you. But just a few comments. So because there was this the previous workshop on zero-shot learning, so why do we need to bother at all with all those task-specific models and task-specific pipelines if you can just write a zero-shot prompt and it seemingly solves everything? Any guesses? So Anders already raised this issue of controllability. For instance, of course, similarly as GPT models just guess the next words or subwords, actually, those language understanding models like BERT and some classifiers trained on top of BERT, like for instance for part of speech tagging or syntactic parsing, they are also just guessing the most probable part of speech category, the most probable syntactic function for this word. But this guessing is more focused and can be more controlled and controllable. It's still guessing, but in a more controllable way. This is for one thing. But then perhaps from the very pragmatic point of view, it costs nothing, actually, running such BERT model. And you do not need to take this gaming computer from your kid to do this. You can do this on your own CPU. So these models are very, very, very cost-effective and still efficient for those specific tasks. Okay, this is a specific task, syntactic parsing and part of speech tagging, but still there is quite a large set of use cases where to apply such a generic tool. Okay, the task. But before I explain the task, maybe there are some questions so far. Yes?
Yes, I like control. So I don't really trust those new models, but they perform so good, so I have to use them, but I don't trust it, and I feel bad about it. So I was thinking, is it usual that there are some phrases and some sentences that are so common that they're actually hard-coded, that in this case, model, don't guess, check the dictionary, we have already solved this with 100% accuracy. Do you understand what I'm asking?
So you are seeking for don't guess if you know, but otherwise guess.
Yes.
Well, this is not how those models work. They're guessing all the time. A vanilla model as such. Of course, you can then make some hybrid approach, try to make. But how to decide if this is the case which is known or that should be guessed? But of course, if you can start with some. First of all, you can start with the lexicon, for instance. Can I find this word in the lexicon and then know all the morphological and lexical properties about it? If not, then, well, let's guess this new word that has appeared in this text.
Is it how it's happening in your practice that you have lexicons of some fixed words and the model is not guessing? It's still guessing everything?
In case of, for instance, in case of morphological parsing, first of all, the model gets, yes, it actually gets the lexicon and it understands it gets some knowledge about words. But this lexicon is limited, of course. And if there are words which cannot be found in this lexicon, then it has to guess, oh, it's a new word. It looks like a verb because the ending is this, or because the context is like that. But even though if the word is known from the lexicon, there's still, especially for inflective languages, but not only for inflective, also for English, you have to understand, is it a verb or is it a noun in this context? And you cannot put in lexicon this specific knowledge. You have to guess it from the...
Yes, I'm giving up the control, hope.
But it can be a controlled guessing.
Maybe some more questions?
It's already further going deeper into the topic, but I know from some lemmatizers and part of speech taggers that they do not good with guessing of words that are used very rarely or are unique words. So some authors invented words, but they make perfect meaning to the human reader, but parsers, sometimes, like taggers, sometimes don't know what are those words, and they guess the part of speech not correctly and the lemma not correctly. With the language models, how do they do with words that are used very rarely or even are unique?
Yeah, well, first of all, this is again, remember that all those models work with some accuracy. And it might be the case, yes, that those earlier words have not been seen and the model might get them wrong. But it's not necessarily the case. There might be specific features that are actually very significant to specific classes of words, etc. But I think the conceptually, what we must understand and keep in mind, that those new large language models are not handling our text word by word as we are doing. They are actually looking at very small sub-word units. In English, those units might be larger in case of, for instance, GPT-4, but the same lexicon is also used for Latvian. And since Latvian in this training data sets has been in a much smaller amount, then Latvian most likely will be analyzed often just character by character. The words are analyzed character by character. And so it might be the case that, well, actually this word bears meaning from one word, the stem part, and then the ending means something very similar that a word would mean, verb would mean, or noun would mean in this context. And so it's not, the analysis doesn't happen just word by word. Does it help? well, most likely there will be questions where we get hands-on. So the task that we will try to solve today is that we will create a teeny tiny multilingual grammatically annotated text corpus. And by grammatically, I mean this by using this universal dependency grammatical framework for this. But instead of parliamentary corpora, as was in this example, we will create a small media corpus. Each of you will select some language, well, preferably your I don't know, your native language or some language of your interest. So hopefully we will get quite a diverse set of languages there. And well, your task will be, at least for the beginning, to collect some 10 articles from some news portals, and we will see how to do this automatically. This both the collecting part and the reading part or scraping part from those web articles. But together we will create a single multilingual corpus. So you will submit many small corpora. Each of you will submit one file to a specific place. And then we will concatenate this together in a single corpus file. We will upload this into a NoSketch engine instance similar to that one that was shown in the slide. And then hopefully you will be able also to make some queries both in your data and also in the data that others will have prepared. So where will we get this data? Yes, we were figuring and thinking which would be a good source where to take those 10 articles for each language. And well, for instance, in Europe there's Deutsche Welle, there is BBC who are producing news in many languages. But it's not that many languages at the end. It most likely wouldn't cover all languages of interest, and also it would be technically a bit difficult. So therefore, we will use such a site which is or a tool which is called Europe Media Monitor. I will show you, so you will see it later. And from that media monitor, we will download some 10 or more articles to process. And for this we will use one already existing high-level Python library. So basically, you will just need one or two functions from this library to run. Then the next part in this tedious part of this hands-on session will be to extract actually text from those web pages. Because as you will see, there is not only text included in the source of those web pages, there is a lot of stuff all around those sites, which is not necessary, and actually which would make noise for our text corpus. So we will need to extract only meaningful text parts. And again, we will use some readily available library for this. We will do this extraction in a very naive way. Of course, in reality, it would take much more effort to really extract quality text, but we will do this in a quite simple manner. And then the second library that will be used will be this stanza framework, which will provide this uniform morphological and syntactic parsing means for I guess that for all the languages that you will try to process, but let's see, maybe there will be some language for which you will not be able to find articles or which will be not supported by stanza. So. Yes, and then hopefully we'll make this concatenated file, which will be uploaded by us to a Corpus platform, and you will be able to try this out. So maybe we should take a quick break before the actual work, but just information for those who are aiming for those credit points and who would like to get a grade. So what will be the criteria? So first of all, so what you will have to submit is, so there will be once a single draft Python notebook that we will all be working with. But so then your task will be to make some little improvements, little additions. Also, this notebook is intentionally, it doesn't contain any comments. The code doesn't contain any comments. I will explain, but your task will be to write your own comments. Otherwise, if everything is already commented, you're just clicking the run buttons, and so this will hopefully force you to try to understand what's happening there. Also, please keep the runtime output so that we can see the runtime output already without running your code. This is one thing that has to be submitted, and then also this corpus file that you will create also should be submitted as well. And then, well, some criteria how to get these grades. So basically, if you will manage to run, this notebook is already self-contained, so you can run it through and get some results. And if you're able to do this with some little tweaks for maybe for this or that language, then this will be enough to get already a good grade. But then, of course, for some extra points, then just pay attention to this particular slide. These slides are also available in that GitHub repository. And then for the maximum grade, just surprise us. So for instance, well, it could be, for instance, just scaling up your corpus from 10 articles to 100 articles. Or maybe you can try, if not zero-shot learning, then few-shot learning. Provide some examples with already annotated, syntactically annotated sentences, like 3, for instance, and then ask the GPT or other model to annotate syntactically according to this universal dependency approach and according to the CONL data format, some new sentences, for instance, or use some other framework if you're an experienced programmer, and so on. Any questions about this important part? Nope. Then, yeah, let's take a little break and maybe 5 minutes or so. Okay, then let's move on with the hands-on session. So we will start from a GitHub repository, and the link to this repository is given in those notes for the workshop. So there is the link. Did anyone find this? And if you found this, then this means that you are in this repository. So don't worry that there is something in Latvian. This is a repository of an NLP course at our university. But at the end, there is a section on this summer school, and there are both slides that we showed earlier. So you can consult those slides as well. But then there is this draft notebook that I mentioned, and for those who can still work in the Colab environment, just click on this Open in Colab button. And for others, I hope that you have managed to install locally. So let's begin. Yes?
Can you maybe slowly go the steps again? I feel some people miss the steps.
The steps for the task? Or? Okay. I closed that Google document, but there is this preparing for workshops document, right? And then there is a link to this GitHub repository. And click on this link and open this this BSSDH notebook. That's number 14. That's number 15. Number 15, yes. Number 14, these are the slides. And then it should look like something like here. So can you read this? Or should I make it a bit bigger? Okay. So first of all, as I said, we have to do this the tedious and rather dirty work of getting the content for our analysis and to pre-process that content. So first of all, the question is how to get those 10 articles. Of course, if we are looking just for 10 articles, you can go to the news portal, copy those links in a list, and that's it. But if you are going for 100 or 1,000 or 100,000 articles, then it's not anymore feasible to do it just by copy pasting manually. And therefore, you need to deal either with web crawling. This is mentioned here, but we will not do any web crawling here. So just to do optionally if someone wants to feel that everything else is rather simple. We will go an old school approach here. So it used to be that news portals provided those so-called RSS feeds or feeds that to which you were able to subscribe. For instance, we are your email application, and then those latest articles just were ingested into your inbox. Here we will use the same approach, and it turns out that this Europe Media Monitor that we will use, and you can click on this link, Europe Media Monitor, and most likely something like this will open. So this Media Monitor, this is a tool hosted by European Commission, if I'm correct, which ingests on a daily basis, on an hourly basis, or even more frequently, it ingests news articles from many sources. If I recall it correctly, about 200 articles per day or something like that. And then those articles are clustered together into news stories because different portals are actually talking and reporting the same events that are happening. And here you can see that, well, there was one event, for instance, related to what Biden just said, and then this story is continued by other news portals, many, but this still is a single cluster. And so this was just for the context. Nevertheless, what we can get from here are links to those articles mentioning those currently trending stories. So your task will be to create a small corpus of currently trending news events and topics. And for that, there are those on the side. There are two links: top stories and 24 hours overview. And if you click on that, for instance, the current top stories, current top 10 stories, then on the other side, here is a set of languages in which those current top stories are available, including Latvian, for instance. I have chosen Latvian, but you can choose another language, and whichever you like from these. And then there is a small RSS button up here, link, RSS. And if you click on this RSS, it opens a new tab. Sometimes it takes, for some reason, this server is not that very responsive sometimes, and it takes a bit more time. It should be quickly. Yep.
Sorry, I got 503 service term per
Well, strangely. Right. So we are very lucky. This service is unavailable temporarily. Yeah, that's a bit unexpected. Okay. If so, we will need some fallback solution, and this fallback solution most likely will be that We'll switch back to manual copy-paste collection of those news article links. Sorry. But this is a VPN. So, but that means that this local Wi-Fi is very restrictive, or in a blacklist. Okay, let's try it out.
What you can do is the link in the code has the variable for the language, and if you just switch the language, it automatically gets the articles in the language you want. So all I needed to do was just to switch English to Romanian, and it automatically parsed everything.
So, but those you got those RSS feeds, right?
No, I didn't actually need to get them because you go to the code in the callout.
Yes. You mean this? This?
But yeah, the language is a variable. If you just
Yes, yes.
change to LV or Pro or whatever language, it will automatically get.
So, but this was. I tried to do this, but this was not working with this Wi-Fi. So, for instance, English or Latvian here.
No. I meant just in the callout code.
But it works from Collab, yeah.
So if you just run the code.
Well, anyway, I will switch to my mobile data. Let's see if this was the problem. Yep, this is indeed the problem with the Wi-Fi, not with the media monitor service. Quick solution, those who have mobile internet, please switch to that one. Otherwise, but yes, as you mentioned, maybe this extraction of those RSS feeds will still work from your Collab. Let's see. But nevertheless, so what this RSS feed contains, this is just a structured XML file. There is a lot of things. This is a very standard format, an old format, but from all this information here, so there are 10 or more articles, those currently trending articles. Well, not necessarily 10, but a bunch of currently trending articles. But only this element link is actually what interests us. So we would like to automatically collect all the currently trending links. Okay, so this is the source where we will get this data from. So going back to this slide, yes, so media monitor, current top 10 stories or the biggest 10 stories over the last 24 hours. You can switch between those two feeds here in the code. If you want to know more about this RSS format and the way it was developed and what's the benefits of it, then there is a documentation, but we don't need to go into this detail now, for now. And to parse this XML document and to actually get those link elements that we are interested in, we will use this feed parser library. And to get that library from Collab, just run this, or from your local computer, just run this install code. It should be quickly done. And now let's import this library. And we will also import some supplementary tools which will be helpful a bit later for parsing those URLs and for counting things. Very useful libraries. Now, the first thing is that so how to automatically extract those link elements from that online web service. So yes, we will use this feed parser and the parse function from it. And this function or this method expects that you provide a URL to some RSS feed. And this URL is what I have copied here, those two versions, the currently trending and the top 10 top stories in 24 hours. You can then by default, this is this current feed, but you can change it to this other variable if you like. And I suggest you to do this to compare how many articles there are in the one feed and in the other feed for your language of interest. So the English is by default, but please change it to some other language. I will change it to well, I will actually leave it for English so that we can better understand what the output together. Okay. Yes. Oh, okay. So the this news, this media monitor. So I selected, for instance, top stories here or top 24. Selected language here on the other side, and then there is this small somewhere here RSS. Can you see it? You can't click on this R? Ah, okay, and I'm clicking on this RSS, and it opens this this XML file, which contains currently a list of currently trending. And the link is so here is item, all those currently trending stories, and for each item has different metadata like title, some keywords, etc. We are interested only in this link element here.
So the link is specific to
To a specific news portal, specific article. And here is article from one portal, Jauns.lv, and here will be from DNLV, and so on and so on.
But we copy the whole thing.
So if you are using this feed parser library, so we are not copying anything manually, but what we are copying automatically are just those link elements. This feed parser goes through all items and takes only this link. Well, in our case, we can take whatever we like from this. But here, so let's switch back to the code. Here, what I'm actually picking out. So I guess that you're already familiar with this for loop in Python. And what we are doing, so the feed parser returns from this URL some object, some dictionary kind of object. And this dictionary contains all those elements as keys. Title is a key in this dictionary, link is a key, keywords, etc. I just copied here the address to the feed, and that's it.
Yeah, but I also copied, but I don't have this line in the middle of this.
Yes. I made this intentionally so that it would be easier for you just to change the language code here from English to Latvian, and then this. So this is a variable. And then this Latvian, what is stored in this variable language is used here. So this is just a little automation so that you don't have to change language code all the time in 2 or 3 or 5 places.
So we don't have to copy that. You have already done it.
Yes. It's everything is done. Yeah, this was just for explanation where it comes from.
How can I undo then?
Controls. But it's not incorrect. No, it's not incorrect if you replaced it. So you have a fixed URL. That's good. If you will stick to that particular language, it's all right. So this is just for convenience. You can use fixed URLs as well. Okay, but what's going on here is that we are going in a loop through all those entries in this RSS feed. So for each entry, we are taking only this link field from each entry, and we are storing it in a list, in a Python list, and this list will be stored in this links. So this links variable will refer to this list, so that later we can refer to this list. And so you can just execute this code, and what we see here, that for, I already changed it to Latvian. Okay, I changed it to Latvian, and we see that currently in this Latvian feed, there are 16 links, 16 stories trending. In 5 minutes, maybe this number might change because, well, time has passed. They have already ingested new stories. Maybe something is old enough to remove from this feed, and some new stories appear. So it's very dynamic with this media monitor service. If we change to back to English, if I change back to English, you please stay with your language of your choice. But if we go back to English, then the list is much longer. So nearly 800 links to some articles. So obviously they are ingesting much more articles from many portals that write in English, and only from few Latvian portals. But that's all right. So, but okay, it might be also the case for you, that for some of you this list is longer than you can handle in this limited time. So how to approach? What could we pick? We could just look through this list and say that, oh well, express.co.uk 1 time mentioned, 2 times mentioned. Maybe this is some good source to start with. Maybe something other. But how to get quickly understanding of which are the most important or most largely covered news portals here to start with. So if I take just out of my mind that there is such a Telegraph, I think, .co.uk portal, and if I try to filter out only those domains, it appears that actually the Telegraph is not among today. Today is not among those articles in this trending list, but there is a Belfast Telegraph, 5 instances. Is it well represented? Does this portal represents the whole media well or not? So I cannot understand it just by picking out some few domains and analyzing. So what we need to do actually here is, before filtering something out, we need to look at the next 2 blocks of code, data analysis. So we will do a little data science here, speaking very boldly. So the question is, which are the most frequent portals currently trending? And for that, to answer this question, we need to go through, not this filter, but we need to go through all this in case of English, go through all the list of those nearly 800 English articles, to write down the domain names, just the globenewswire.com, and not the article part, just the portal part from the URL, and count how many times each portal appears in this whole list. To do this, and you can later on exploit this same method and these same libraries, not only for counting domains, but also for counting words and counting everything that you need. And counting, actually, also as yesterday Javier mentioned, counting is the very beginning of everything, to understand the picture of your data. So let's run this, first of all, run this code. And what it did, so it just outputs all the unique domain names with the frequency counts well, with the counts in this corpus of article links or in the list of links. So we see that this is a domain that appears only once, but then there are other domains that appear 4 times, 4 articles from this domain currently, 6 articles from Financial Post, etc. But again, this is quite messy. We need to sort this and we will start work with those domains which frequently appear in this list. So therefore there is this next block of code, but let's just a few comments about what happened here. So what we did was almost the same code that already appeared here for extracting links. So we are going through the list of links. So these links we already processed, and we stored the links, all this list in this variable links, and we are going through that and using this URL parse, this module here, to actually extract just the domain name from this URL. We could do this in other ways, of course, but this is a very convenient way. So if you would look at the documentation of this library, you would see that there is a method, a network location, which extracts just the domain part of a given arbitrary URL. So at the end, this domains is again a new list, but just a list of domain names. And since we have this list, we will now use this other class counter from that library. And this counter class, given some list of words or list of links in our case, or list of domains actually in our case, will return another data structure, kind of a dictionary structure, something like that, that contains this information about the items that we are counting and the counts for each items. And again, a for loop, this loop which goes through all those items in this frequency list, and each item contains 2 elements, the in our case domain, but it could be a word or something else. So these are just my arbitrary variable names given here, and I'm just printing out that this domain and this count, this is the count of this domain. But this list was unordered, so again very difficult to get the whole picture there. Therefore, here this block is just a little bit elaborated version of this first one, which actually, first of all, we are doing some pruning. We are not including, so therefore there is this condition that we will include. So I will not explain every single detail in this code, otherwise it will take too much time. But the important thing here is that we are taking only those items from this frequency list for which the frequency count is larger than 1. And it's typical, it's a very typical case. Are those domain names, words, anything that in any frequency list, if it's more or less a natural distribution of frequencies, half of the items will occur only once. In a corpus, half of the words or word forms occur only once, and the rest occur more. So we will prune or ignore this long tail of rare domains in our case. And we will also sort this. So this most common method again for this class returns those this frequency list not in an arbitrary order, but in a descending order regarding the frequency count. So if you run this block, and if you scroll it up, then you see that article.wn.com is the most frequent, and similarly those few other appear quite frequently in this English field, but it might be a different picture in case of your selected language. So the suggestion is to start with those. Maybe there's just a single domain that already gives you 10 articles or more to work with, and you don't have to pick from different domains. Or maybe you want to make a more diverse set of data and intentionally collect from different sources. So it's up to you. But the minimum requirement would be at least to take. In my case, I would take for instance this first one and deal with it. So, but yeah, maybe I will take a bit smaller one, like, okay, let's take this business standard, for instance. Okay. And now that we are this data analysis, I got that picture that Telegraph is not at all trending today, but actually some other portals, like this one, for instance. So I will update this code, run again. And I see that, yes, here are those 12 links to the business standard portal with those 12 articles. And what happened here is pretty much the same as already explained in that previous block, but just with this filtering. Again, we are filtering and taking only those links which contain our filter condition, filtering criteria. So only those links which somewhere in the URL contain this string www blah blah blah.com. And this narrowed down list is stored in this filtered links variable to be used later on. Well, maybe, I guess that there might be some technical nuances that maybe are not clear, but at least conceptually, is it clear what was done? Okay, great. Then let's move on, because our task is first of all to run through everything, get some dirty results, noisy results. Let's say noisy, not dirty, but. And then we'll upload this to the Corpus platform and see what we already achieved. And then in the next iteration, you will be able to fine-tune this code to make the better data selection or better cleaning and pre-processing part. Okay, so just remember that we have now stored some narrowed down list in this filtered links variable, which contains this Python list, or refers to this Python list. Now, the second task is to extract the useful content from those web pages. So let's see what I'm meaning by this. What are useful? What is useful content and what is not useful content. So let's open just in my case, so I'm using this Business Insider. In your case, you will have some other portal, but nevertheless, I'm opening it. So this is the article. Okay, so there is some content here, the actual article. Then there is some sidebar, which we are not interested in. This is not part of the article. There is some menu. This is also not part of the article. And then there are some related articles, advertisements, everything else that is not part of actually this specific article. So, but how to extract that text? So we will actually download all those articles to your, well, either locally or in your Colab environment. And we will have to parse them. And what does it mean? So if you click the right mouse button on that web page, there is a view page source. Well, this might be called differently if you have a different browser, but you can view the source of this page. And if you view the source of this page, oh my God, what's there? It's full of something that we are totally not interested in. And somewhere in between there is some useful stuff. So let's try to locate that useful stuff by looking back at this article where it starts. So let's try to find this first sentence. Google Maps, it's set to copy. And let's try to find this. So somewhere, so it's among this mess, there is somewhere this useful content. And then seems that there is a next paragraph, and then there is a next paragraph, and so on. Well, some of this is useful, some of this is not, but at least we have noticed that in case of this particular portal, those div elements are what we are at the first glance looking at and searching for. So most likely that in those div elements will be some useful content. Also some some garbage from text perspective, like all these style definitions, etc. Which for some, but these will not be contained in those elements. Good. This is just that this, in my case, this specific HTML code is not well structured, so it looks very messy. So this is the task, to extract just those useful segments from this HTML document. So how to approach this task? So first of all, technical part, we will need to download those web pages. And for that, we will use this requests library, a very elegant and simple to use library for making those HTTP requests and downloading content. And therefore, we will need to install this library. So let's run install requests, but we are also installing a fancy library called Beautiful Soup. So this will help us to do the actual work, but we also need this technical library as well. So when it's installed, then we will import this Beautiful Soup parser and also the requests library, but we will also use JSON. The JSON library, this is the built-in library in Python. We don't have to install it separately. Why JSON is also needed you will see later. Okay. So now let's focus on this, why we imported such library, so this Beautiful Soup library. So this is again a high-level API that will help you to extract those useful parts of web pages and filtering out everything the rest that you don't need. At least we will try to approach this. This is not that easy actually, but we'll see. It depends also on the particular portal website, how they design those their web pages. Some of them intentionally try to make it very messy. Well, maybe not intentionally, but at least this is the effect, that it's very difficult to extract. And some of them are very nicely structuring and making some labeling classes so that you can very easy to extract good content. So, but nevertheless, there are two strategies. First strategy is take this web page as it is, all this HTML code, and try to remove the unnecessary elements, hoping that the rest will be good content. Or the other way around, and you can combine, of course, those. Try only to pick some useful elements and ignore the rest. So, first of all, we will try this second approach. And the second thing to keep in mind is that, so you will, at the end, we are trying to notice some patterns, some frequent patterns, and we are trying to use those patterns in this extraction task. But then what works for one portal might not work for another portal. And then most likely there will be some domain or portal specific patterns, and there will be some common patterns across all portals and domains. So you just have to keep this in mind, that this extraction part in real life will get the code will get ugly at one point. Yes? Oh, the pattern, for instance, by pattern I mean this, that in this case, in this business standard com portal case, they have the pattern that useful content typically is stored in those div elements. In other case, maybe this will be the paragraph element, which will be used to store useful text or some other things. But it's not. But this is just the first guess. Other portals will have this element with some class, and then you have to look at that also. The class, is it useful or not? But first of all, so my naive guess out of the blue was that maybe the paragraph element is the most typical one to look at. In my case, I have to change it to this div element that we will be interested in those blocks of the HTML code in case of my portal, in this business something portal. In your case, maybe, so you have to look at the source code and try to locate very quickly what looks like the most typical element where text is stored.
Sorry, can it be like 5 names?
Yes, well, but in that case, you have to repeat it for. Well, maybe you can. I'm not sure. Maybe we have to then look at the documentation of this find all method. Maybe Vestus or someone can look at this. Maybe we can provide a list here or a regular expression. Maybe is it allowed? Well, we can just maybe try it. So I can maybe say that either this element or this. Let's see if it accepts regular expressions. I don't know. So, but what I'm doing here in this tiny block is that first of all I'm getting this HTML code. We are this requests library and the method get, and I'm providing just this URL. Well, currently this is just a definition of a function which will be called later, but nevertheless somehow this URL is provided, and the content is extracted. So this response variable contains the actual HTML code. And now we will pass this actual content, so response.content. So this content field actually contains this HTML code. We will pass this to the beautiful soup parser, to this HTML parser, which we will use for parsing this content. And now, in my case, so maybe I should rename these paragraphs to something else, but it's not in. So this is just a variable name. Maybe segments would be a more general name here, but you don't have to rename it. And so what I'm trying to do is find all elements which correspond to this pattern. Well, let's see if regular expressions are allowed here. And when so this again will return a list of all those paragraph or div elements in our web page. And then what I'm doing here is that I'm just joining all those elements that were found in a single string. In a single string, which is where each of those segments is separated by a new line character. So let's see if it works. So this code does not output anything. This is just a function definition. Then there is actually this other block of code which does the actual part. Yes. 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 Okay. Does the term regular expressions ring the bell to someone? At least to some of you. Okay. Let's forget this term. This just means or. How do I insert? Press Shift, hold Shift, and then somewhere near the Enter is a vertical bar.
Do we have to put both div and pair? Or pair, or because I tried both of them?
Yes, and it didn't work?
It works, but with only pair, I have the cookie policies. All a list of cookie policies.
Yes.
With the div or pair, I have some lines, only lines, without text.
Well, therefore, first of all, let's just don't use all those alternatives. Just let's take just one element, P or div or something else, and let's see what happens, and then we can try to improve this. But first of all, yeah, you might get something that maybe is not very useful, and then you have to look again at the source code and decide what fine-tuning has to be done there. But nevertheless, there is this second code block where we actually will produce the data set for later processing. And by data set, I mean just a list of plain text segments. So what we are doing here, so we are going through the list of previously acquired and filtered links, so the short list of links. And for each link, we are extracting the plain text, the content, what will hopefully be a useful content. And we are calling in each iteration, we are calling this extract plain text function here and providing this specific link. And this is one thing. So we are just extracting this text, but then we have to store something for later processing. Of course, we could just store it in the memory, but well, let's store it in a JSON file. Again, a very typical format where to store something for later processing, because, well, maybe tomorrow you would like to continue, and then this object will not be available in the memory anymore. Therefore, we will create a JSON file which will contain a list of article elements where each article will contain those 4 fields. Language, and the language, therefore I introduced this lang variable, not fixed URLs, etc., because we are using this variable also here. So whichever language was set in this variable will be stored also in the JSON, English, Latvian, or whatever. The domain, again, this domain part of the URL, the actual URL, and the content. And so at the end, we will get such a JSON file. And it will be stored on the file system, well, in case of Colab, in this Colab environment. So let's run this code. So seemingly nothing in the output. But in my case, I switched back to just this one element. Let's see once again. Let's look back at my code. Oh, well, yeah, it's a bit strange as always, but let's. Oh, okay. It turns out that there is a fancy method supported, which will significantly make things easier. So instead of finding some specific element, okay, let's try this one. So I will comment this out. Actually, yeah, this is what I will need. I will comment this one, these both lines, and let's write it differently. So the element text will actually how we will get this content is that we will use this soup object, and we will. So there is a get text method already at the top level. So instead of creating a list and joining something, so I can just provide the so the separator will be, well, let's say new line. And strip most likely will mean that we will get rid of unnecessary white spaces, etc. So it might be the case that this single line does automatically everything for us, and we don't have to go into this very tedious analysis of all those HTML source code. So let's try this out. Let's compile again this function. And okay, this was not a problem. Okay, Business Insider is not a good domain for me. I guess that they are trying to deny any such access there, but let's try another domain then in my case, but maybe for you it works. So yeah, but I will leave this. It works. Okay, then, but so for you, just rewrite this line in your notebook. So this is the magic line that solves everything, and we will be able to move on to the next part much quicker. Yes. But you put it as the third line.
Yeah, as the third line, yeah.
And it doesn't work at all.
And now it doesn't work. It gives me exclamation mark. Before I got some news items.
Maybe Arthur, you can check. Maybe is it a syntax error that is thrown or just empty output? Then most likely some syntactic error. I will enlarge this line. So, but I hope that most of you have managed to rewrite this line. Yeah. Okay. Then let's move on. So I will change. So since this this business standard com is not very open, I will switch back to this I will switch back to this in my case. I will get only 5 articles, but that's okay. And let's see what happens now. Hola. Well, this is at least something. Of course, as you see, there is some noise as well. There is some. The title has been extracted. Date. Well, it actually see. I don't see the actual. Right. Yeah. True. So more or less, I guess that. So let's see if there is a useful content. Yes, what we can very quickly see here. So this was actually not a magic method. So it just extracts all the text, all the labels of the buttons, of menus, everything. So this is a very noisy text. But let's move on. So so in that case, maybe, or maybe let's not move on. Let's actually go back and. So I changed my mind. So this is not actually something magic. I'll switch back and I'll try out just to pick out not everything, but just, well, my guess is that maybe these paragraph elements will work. But as you see, this is the real life. You have to experiment and try, and there will be errors and until you get something useful. Okay, finally something that looks like a normal text to me, at least from. Okay, so what I did in my case, and which works for this Belfast Telegraph and maybe for many other portals, is that I will just take all the paragraph elements, get text from those only from those paragraph elements, and not from all the elements across this document. And each paragraph will be stored as a separate paragraph in this output document. But don't worry if so this is just for our quick analysis. This is not the actual output. The actual output will be stored in the JSON file.
I was emulating you and now I have error. It was working.
And what kind of error?
I followed you because mine was also not.
Yes.
As I wanted, and I uncommented them.
Yes.
And it became right.
It seems that this the indentation has to be the same as for the first lines. Try now. Okay. Is this the case that you are getting some meaningful text? Okay. Great. So this output actually was just for quick testing, if you are getting something or not. Now that you are convinced that there is something useful, we can remove this temporary output. But actually, at the end, there was writing in a file. So with this open corpus JSON, so we were actually this piece of code created a JSON file. So if you click on this folder icon here on the left side, you see that there is a corpus JSON file that has been created. And if you open this file, double click, you see that what you did, you generated such a JSON file. In my case, language English, domain Belfast Telegraph, link to this particular article, and then the whole content of this article. Well, not the whole, but at least what was extracted, given this tiny rule set of just one rule, extracting the paragraph elements. Okay, so far so good. So we are now through this first part of getting hands dirty, and I think we all actually managed to feel this. So let's move on to the next section, which is creating an annotated text corpus. So now we have this. Yes. It should be stored somewhere in your default location, which is, who knows? Mister, maybe you know? Mm-hmm. Yeah, maybe you can try to help. Okay, but at least those of you who are working in Collab, this file has been created and stored in this default location. And now, more questions? Or we can proceed. Okay, let's go on. So now we will actually do the syntactic parsing. And by syntactic also I mean both morphological and the syntactic parsing. So we will use this, this stanza library developed by Stanford. So those of you who are following, first of all, let's install stanza, and I think it will take about a minute or so. So let's run this installation process. So this is quite a large library. Done for me. How about you? Have you installed? Okay. So I will delete this output. And now once the library is installed, we will import it. It should be much quicker. Okay. And now, so we have imported the stanza library. The next task is to download and load the model, a set of models for our language. So in my case, by default, this is English, but you should choose to the language that you selected. And this, so how do you know if, first of all, how do you know if your language is supported? So first of all, so in this documentation bullet points, click first of all on this first link. Available languages and models supported by this stanza framework. But since we will be, available languages and the available UD models. So we will not be interested today in named entity recognition or sentiment classification, just this grammatical part. And if you scroll down, yes, there is actually a performance page. Available, so there is a section available UD models, and then there is a link to performance page. And if you scroll down, so there is a long list of languages. So try to enter, to filter your language, like Latvian, for instance, and you see, first of all, you will see if your language is supported at all. What is the language code? Well, most likely this is this unique, ISO 2-character code for the language. So LV for Latvian, N for English, ET for Estonian, and so on. So are you all happy in terms that your language is supported? So there is no language which is not supported. Nice to hear. So it was worse to choose this stanza framework, therefore, even if the accuracy for some languages is not that high as in case of other frameworks. Okay. So please download and install your models. This should be pretty fast depending on the network connection. But as you see, so the English model, for instance, is about 500 megabytes. Small or big? Well, much, much smaller than in case of some really large language models. So it's done for me, at least. So now we are approaching the actual part. Now we have to create a pipeline, a processing pipeline. So in our case, we are interested in this grammatical processing, which includes sentence splitting, tokenization. For each sentence, we need to tokenize it into words and other tokens in the sentence. Then we want to assign part of speech tags to each token, also lemmas to those tokens, the base forms, and we also want to add those dependency labels. So we will not work with the full syntactic trees, but we will at least parse and get those dependency labels for each token. Is it a subject in the sentence? Is it an object, or etc.? So, but how do you know what pipelines, what processing pipelines, and what processors are available for this framework? Again, you can consult the documentation, supported processors and pipelines here, and if you click here. So what we see here, well, basically this is the documentation of this, some kind of an API documentation. But I will scroll down to the processors. So for all languages for which these UD models are available, UD-based models, a tokenizer is available because this information was encoded in the universal dependency tree banks for every language, and therefore this, the model was able to learn this for each language. Part of speech processor, which adds those part of speech tags, lemmatizer, dependency parser, also for some languages, but not for all. For English, for instance, named entity parser is also available, but we will not use this. But then for other languages, these processors are not available. But then, okay, so since our ultimate goal here is to get those dependency labels at the end of the pipeline, so in the documentation, as you see, these are the requirements. Which processors must be run before, so that we, at the end, also do this dependency parsing. And these requirements are that we have to run the tokenized processor, also this multi-word token processor, which we will not go into detail, but this is just a requirement here, and we will include it. Part of speech, tagger, and lemmatizer. And if we switch back to the code, you see that I'm creating a pipeline, and this will be referenced by this NLP pipe variable. But so from Stanza, I'm using this pipeline constructor and providing, again, my language. Actually, here I could use this variable that I created before, and maybe also here, to make the code more flexible. And this is the list of processors separated by comma. Tokenize, MWT, POS, lemma, dep, parse. So you have to use exactly those names. And let's run this code. Okay, the pipeline has been constructed, and we see that all those processors are loaded into the memory. We also see that since we did not specify in the Colab environments that we will use a GPU, it will by default use the CPU, but this will be perfectly fine for us. And yes, done loading. Did you receive this message? Done loading processors. I will clear this. And now, since the pipeline is created, models are loaded, everything is done, and ready to do the processing, the syntactic, the morphological and syntactic parsing. But, so remember that we stored that text corpus that you extracted in a JSON file. So first of all, before actually doing this processing, we need to load this corpus back into memory, and therefore there is this this next block of code. Just run it, and what it will create in the memory, it will create a list which will be referred by this corpus variable, and this list will contain this will be a list of dictionary objects. Basically the same objects of the same kind that you stored in the JSON file. So we will create a list of article objects. For each article there will be a field language, domain, link, just a metadata that we will use later. But for now, the important part is that we are introducing a new new field, which in your JSON file, this was just a text field, a plain text. Now you could still call it text, but so I'm intentionally naming this document. Since document in terms of Stanza and other frameworks, if we look back in this documentation, what Stanza objects there are. So document is the top level object that holds annotations of the entire document. So a very general name for this kind of an object. But the point is that this field will contain a document object already parsed structure of your plain text content. So it will be sentence splitted, it will be tokenized. For each token, there will be assigned a part of speech tag, a lemma, and a dependency relation, among other things. If it's not working for you, then again, this is the how the JSON file looks like. This source, the JSON file that we are now importing and constructing this memory object. Okay. Okay. I hope that so far so good, because now we have loaded all the processors, created a pipeline, loaded also our text, our plain text. Actually, not only the plain text corpus. Now we have loaded already a processed corpus, which is stored in those in those document level objects. So, actually, all the parsing has already happened. So, did you manage to run this this block which starts with corpus as an empty list? So if you manage to run this block of code, then all the parsing already happened. Now we will read the results of that parsing. And this will be the hopefully most interesting part. So first of all, we will create we'll try to create this standard conll kind of a format from this parsing output, which I mentioned on the slides, and which is kind of a standard data exchange format for tree banks and for syntactically parsed data. So the next block of code, so this conll output, this will produce those. I'll switch back to that slide. So this will produce kind of that output files. Here is the link to the universal dependencies documentation. And here you see that the conll format expects that there are 10 fields in such a file. So there is the index of the token in the sentence, so the first word, second, etc. The actual form as it is used in the sentence, the lemma form, the universal part of speech tag, and we will be using only that one. We will ignore this language-specific morphological tag, which might include much more information than just a part of speech, especially for inflective languages. We'll also not use this feats or features field, which also Stanza provides for us. We will use this head, which means which is the head element in the sentence on which the current word depends on syntactically, and we will also use this dependency relation field, which stores the actual syntactic function of this word in the sentence, subject, object, etc. And we will ignore the rest. So, we are again opening a new file, corpus.conll in this case, not JSON, where we will write this conll style of output. And for each article in this memory object that we call corpus here, which is the list of those already parsed articles, so we'll iterate through this list. And for each article, we will pick just this document field from this dictionary element, just this parsed document. And we will extract all the information from there. So the document is the high-level object, which contains, if we would look, so what this document level object contains, among other things, it contains a list of sentences. So this we gave just a plain text content, and then this stanza parser decided where are the sentence boundaries. It's not the case that always a full stop means a sentence boundary or a dot. So we will, now that we are iterating through articles, the next thing for each article, we will iterate through the list of sentences. So just we are asking, so we are retrieving from this document object a list of sentences. So for each S or each sentence in the list of sentences for this particular article, we will make the next iteration. But before that next iteration, we will print out this kind of a annotation line in this output file, which will contain the whole sentence. So text will be just the whole text of this sentence. And again, we should then how do I know that I need to write text and not some other name? If you look at the documentation, what the sentence object contains, so among other things, there is text, which is of type string, so just a string. But then there are other things for this sentence element available. Let's see. So now the main thing that we are interested in is that this sentence object essentially is just a list of words. But again, a list of parsed words for which some additional information will be available. So the next thing that we are doing here, we are iterating through the words of that particular sentence. So for each word in this list of words. And finally, we can write the output. And the output is just a tab-separated list of fields for each token or each word in the sentence. So first of all, we will write out this ID element as expected by the conl.u format. So first is ID, form, lemma, etc. And here we are doing the same. We will extract the ID part from the word ID field, the text field, the lemma field, the universal part of speech tag field. Again, if you would consult this documentation, what the word object contains, it contains all those different fields. ID is an integer, text is a string, lemma is a string, part of speech tag is a string. And then this dependency relation is a string. Head is an integer, and we will see why. Well, it's a pointer to the head word for this particular token in the sentence. And we are just writing a single line. I have splitted it onto several lines just for better understanding, but otherwise this whole block just writes down a single line and a new line at the end. And for those fields which we will not use today, I'm just putting these blank values there, so that I have a valid conl.u file. So let's run this. For me, it took only 0 seconds to execute. So as I said before, this is a no-cost game here. You don't have to pay for GPUs, etc. But of course, here it runs very quickly because all the parsing was already done. Now, if no errors were thrown here, please look again at your folder of the output files, and you see that a new file appeared here. And if I open that file, so what I have here is, so there's the first sentence of first article. This is the text of the sentence that we extracted from this sentence text field. This is the first token, the actual word, the lemma, the upost tag, then those blank fields which we are not using. Then it is the index of the word, which is the head word for this token, and which is number 7. This is a verb, so the root or the predicate of the sentence. And so this is most likely the nominal subject, yes. So this is the information that we needed. And if you scroll down, then the first sentence contains 26 tokens, then there is a blank line, and the next sentence begins, and so on. All those, in my case, 5 articles from Belfast Telegraph, all the sentences from those 5 articles are here in this file. Is it also a success for you so far? Yes. Okay, good. So this was just a warm-up phase. So we are able to produce something that can be given to other teams, and they will know what to do with the convol file. They will know what all those fields contain, and etc. But in our case, so our task, remember that we want to, in the rest of the time available to us, we want to play a little bit, at least or later, with a corpus platform where our combined corpus is uploaded and we can do some queries. And therefore we need to create, instead of convol file, we need to create the so-called vert file, but again, it's just a tab separated, very similar, conceptually very similar, just technically a bit different output format that is expected by this corpus platform that we will use, but other corpus platforms use something similar as the input format. Of course, one thing would be to create a converter from convol to vert, but in our case it will be easier just to copy, paste, edit. This was what I done here. Copy, paste, edit of this code that generated convol output, and now it has been modified to generate a vert output. So, but again, first of all, let's consult this documentation, what the vert output means. So let's go to the sketch engine documentation. And as you see, the vert file is something like this, where so we are moving back to not HTML, but some general markup format. It's also not XML, not HTML, but something some familiar notation you can see here. So each document or article in our case will be wrapped in a doc element. So this is the opening part, and somewhere down is the closing part. So here the concrete doc ends, and then the next doc will start. Then there are some document level metadata, and this is up to us what this metadata will be. In our case, so remember I intentionally used and copy pasted all those fields along, like language, domain, link. This will be our metadata for each of those documents. So we will preserve what language it was, from which portal it came, and which was the particular link to this article. This will be our metadata for the document level element. And then we will have, for each document, we will have a list of sentences, and each sentence again is wrapped in this S element. It begins here and it ends somewhere here in this example. Otherwise, it will be very similar as in the convol case, but just a little bit different format. So it will be again tab separated for each token. There is a token, a part of speech tag, the lemma for this token, but we will add more fields to this. We will add also those those syntactic annotations as well. So therefore, what we are actually creating here so we are creating, so for each article again in this corpus list in memory that we loaded before, we will iterate through the articles. For each article we will open a document element, but then there is a to-do task for you to add this metadata. So I will write here for me, but you can then write down for yourself as well. So what we will use, let's see. So therefore, the thing is that we all need to use the same names for the parameters. We need to use the same order of fields for each token of the annotation fields. Therefore, please consult this configuration file. So our corpus platform, the engine, expects, so we have already prepared the configuration file for this corpus that we are now creating, and it expects that at the document level you will have such metadata, such fields as language, portal, link. So these three. Okay. So what I should do here is so I'm writing language equals, and here I will put article I have to use double quotes because single quotes are already used there. And so the language element will contain this field language. The portal element will contain field domain, because I named it domain here, and link will be the same link. So language, the value of language I'll take from this article element, the value of language. So be careful. Language seems okay. Now copy, paste, edit. So the next was portal. Portal is the next metadata field, but in this case I'm taking domain from our in-memory object. And finally, the third is link, which I named exactly the same link. Okay, should be all right. Now, now we have to iterate through the sentences of that document. So here again, I'm taking this similarly as here. I'm taking the document object for that article, and I'm iterating through the sentences. At the beginning, I'm opening the sentence. At the end, this sentence is closed, and then at the outer level, for this first for loop, I'm also closing the document element. And now, similarly as in...
Back a little bit. So why did we say that when there's the portal, then there's the domain? Why domain?
Domain is just because, well, when I wrote this code, well, my guess was that, well, why not call this field in our memory object domain? But then my colleague wrote this configuration file and figured that, well, portal is a more intuitively understandable, and so we need to do this mapping here. No. I'm just you don't have to change. You just have to retrieve the correct element from this in-memory object. So in this case, I'm creating a new attribute portal according to the specification according to this specification, but just the value will be what we initially are referring to as domain. These are just names, nothing else. Okay, and then for each sentence, again, we are iterating through the words or tokens in this sentence, and then for each token, we are creating this line by line, token by token, and for each token there will be a line. And the next question, so the first question was what are the document level metadata fields that we have to create, and the next question is what are these columns here that are expected by this corpus configuration file. And let's go back here. And this is actually the order of those attributes listed here. So the first is word. So we need to provide this running word here. Then the part of speech is the next field. Lemma is the third field. Just ignore those LC fields. This is a technical part. Then the fourth will be dependency, label. The rest three, let's leave them blank for now. And let's see if we will have time for that. Because this will require actually traversing this syntactic tree one level up and extract also information of the parent of our current word or of the head word, which allows us to do some more interesting queries at the end, as I showed you with this Parliament showcase. But let's see if we will get that far. So I will ignore for now this to-do part. Let's leave those fields just with blank values, underscore, and let's run this code. Again.
Can we come back to this line after doc?
After which line?
Yeah, this one that you wrote after doc. We are not ready yet.
This one? Yes. Just to, okay. But those of you who already managed, see the new file in the folder that appeared. This is corpus.vert file. And now, yeah, if you're already done and if you got that Word file, then lower there is a link to a Google directory, and please copy that file, but before rename it according to those naming convention.
Should we rename the file and then add to the Google?
Yes. Yeah, first rename and then copy. Otherwise, you might accidentally rewrite someone else's file. Yes, the Word file. Mm-hmm. There is a link to a Google folder. I just open it, and then you will have to copy the Word file that you produced.
When I try to rename it, it says if you change a file name extension, the file might become unusable. Are you sure you want to change it?
Why not? No, that's okay. But please leave that .word extension. Yeah, that might be the case actually. Yeah. Please leave that .word extension. Otherwise, maybe our script will skip your file. So did you all manage to make a Word file which looks similar to mine. So as you see here, I have generated for my Belfast Telegraph corpus a Word file. So there are documents, first document, then somewhere there will be it's not working like that, but somewhere there will be a next document and next one. But as you see, so the method. So I think I have an error in my output file. I have to regenerate it because I didn't use quotation characters. So as you see, my output is just language equals English, portal equals this domain name, but actually there should be those quotes as well. So this is not correct. Let's go back and edit. So if I remember correctly, but please correct me if I'm wrong. You have to do something like this to actually print out those quotation marks. So just wrap those values in quotation marks. I will check if it works. Yes, now it's what was expected. So language. Yes. It doesn't fit the single line. My screen anymore, but almost. Yeah.
So, people attending timetables might have noticed that officially this workshop is over, but we are being very excited and polite and keep working on. And I'm just waiting for Normans to have some inspirational and formal ending to this workshop. And then I remind you that at 5 people who have signed up to social event, we gather all under, over there, right? Yes, Norman?
So, we almost managed to do all the things, but still we didn't succeed because, so we did the grunt work, we did the actual work, but we are not enjoying the fruits. But also the time is up. So therefore, please still, those of you who want to complete this work, you will still be a little bit around here. Let's try to complete and submit those files. We will then later, by ourselves, create this concatenated version of the corpus, and we will let you know where you can open and play around with this multilingual news corpus. But thanks lots for your efforts.
Oh, thank you, Normand. It was a true delight, and I guess. Okay, let's see. how can I persuade you to come tomorrow again? But I can say that we have just one difficult workshop left in this summer school. It will be the first workshop tomorrow, which will be quite intense, but also something else, something to work with images. And I will send you, again, the last email tomorrow later, where I remind you that you have to look at your Google Colab. If you do not have your credits left, then you have to find a way either to create another account or use some other tool. And also, I will write some information on receiving certificates and deadlines and so on. So if you're interested in that, do not skip this email, which we will receive later on. But today, for those who want, I kindly welcome you to join for a walk. I don't know, is it raining outside? Who knows? I have just one umbrella. But anyway, those who would enjoy a walk and a little talk and enjoying some food and drinks at the Agenskalns market, please meet me approximately 5 o'clock here at the lobby. And if you are not from here, not from Riga, I will tell you some things about culture and history of the city of Riga. And this is really a very nice area. Also my home. I'm a patriot of this side of the river, so I'm very eager to tell you more about it. And if you want to talk about me, about some digital humanities topics or joint projects with the National Library, I will also be very eager to talk to you. So see you later. And for everyone, see you tomorrow again.